Hello everyone. Like I said in the previous video, if it got a positive reaction, I would be making a few more videos. And considering the fact that it is at around 120 views at the time of me filming this, I decided, well, let's not try and make a few more of these and see how it goes, right? So for those of you who liked watching me conduct my little experiment back in the previous video, I think you'll be a bit disappointed here because this video will be entirely theory focused. A fair warning, this video does have a lot of maths. I'll be assuming that most of you watching have a basic grasp of introductory calculus and you're also familiar with integration and ways to integrate basic functions. Along with that, I'm also going to assume that you have a good knowledge of what moment of inertia is, and you're watching this video because you are also annoyed at the fact that your textbook did not give you the reason for why basic objects such as the disk, the ring, spheres, and the shell have the moments of inertia value that they have. I know mine didn't, and when I did look up the derivations for these values, I found them surprisingly easy enough to follow. So I'm going to share them with you here, hoping that you also enjoy what I did. So I'm going to promise to make it as interesting as possible. Maths can get a bit hard to follow at times, but at the end, I believe that it always pays off. Alright then, let's begin. We are going to start with actually defining what moment of inertia is. I'm going to write MOI here because I'm too lazy. So we denote moment of inertia by the symbol I. I is equal to sigma, that is, we are summing up over all the quantities. Mi, that is the mass of each individual particle in the system of particles or like a rigid body, and Ri square, that is the distance of the particle from the axis, that is the line or the point about which we are doing the rotation, and we square that distance. So this is moment of inertia in mathematical terms, but what does it actually mean? So the way most textbooks define rotational inertia, moment of inertia, my bad, is that they say that moment of inertia is the rotational analog of mass in rotational mechanics. But what I mean to say through this is that, like how there is mass in linear mechanics, we have moment of inertia in rotational mechanics. So to illustrate this better, let's just pick a very common question we have in, we have in linear mechanics, that is F is equal to ma, right? So in rotational mechanics, we have a very similar equation, that is torque is equal to I, that is moment of inertia, into alpha. This alpha here stands for angular acceleration. So all the terms here correspond just like this, alright? So suppose I wanted to maintain an acceleration of 1 meter per second square, yeah? And suppose I keep increasing the mass, I would also need to keep increasing the force that I apply. So suppose the mass is around 5 kg, I'll have to put a force of 5 newtons, and if the mass becomes 10 kg, I'll have to apply a force of 10 newtons. Similarly, if I wanted to maintain an angular acceleration of say 1 radians per second square, the torque that I would need to apply would increase linearly with the moment of inertia. So with that out of the way, we can think of moment of inertia and mass as very similar terms, but they're not completely identical. Alright, so let's now think about how one would actually go about evaluating the moment of inertia for a system of particles. Usually when you have a small number of particles, what you would do is that you'd just add up over all the particles that are there. So if you have I is equal to 1 here and suppose n. So suppose I have 2 particles, I would just add up the moment of inertia of those 2 particles. So what I would do here is, suppose this is my axis, right? This is the point that all the particles are going to rotate about. And so here I have a particle of mass m1. I'm just going to make that more a bit bigger. Then I have another particle here of mass m2. And these particles are going to rotate about this point. So what I will do is I have this. Okay, this is supposed to be the distance r1. This is supposed to be a straight line. Okay, just assume it's a straight line. and this is yet another distance, that is r2. So to the net moment of inertia of this system is basically equal to I is equal to m1 r1 square plus m2 r2 square. But what if you have a lot of particles, right? And suppose these particles, well, I'm going to say the term infinite here, but be aware that I'm using it very loosely. Or what I'm saying through the word term infinite is that there are a lot and a lot of particles, and they're all continuous. That is, suppose I have a disk over here, yeah? This is a disk. I'm going to make that more believable by filling it with the color over here. So, hold on, yeah. So this is the disk over here, and this disk has mass throughout. Okay, so the power this is going to rotate about its center of mass that is placed over here. Let me change the color. It's going to rotate about the center of mass that is over here. And so how do you add up all the moment of inertias? Because there are going to be particles at a different distance at each point. Yeah, suppose there's a particle m1 here, it's a distance m2, and there's a particle m2 here, this is distance r2, and keeps on going. And there are lots and lots of particles. So what you do in cases such as these is that you take the limit of this sum as it tends to infinity. And when you do that, you get a very familiar definition. To those of you who have seen this definition, it's very convenient as well. So that sum to infinity changes to an integral, and this changes to a dm, and this just stays the same to r square. So what this thing is telling you is that there is an infinitesimal mass element dm at each of these points, okay, all extending throughout till the edge. There are going to be infinitesimal mass elements, each placed at an element ri at a distance ri from the center. And using this information, we're going to evaluate using integration. So let's just begin with an easy example. We'll do the disk when I believe it's third or fourth. So let's just start with a very easy one. We're going to evaluate the moment of inertia for a ring. So let me just clear all of this up here. Right. So a ring is quite simple in the fact that it has all of the particles are placed at the same distance from the center of mass. So what that does is it makes it very easy for us to evaluate the moment of inertia, right? Because all of them are at the same distance, we can write I is equal to dm r square, yeah, and this limit would be from 0 to m, right? So all of these particles here are at a distance say r naught, okay, and so since they are at a distance r naught, what we can write is we can take this r naught out of the integral, and we can write this as r naught square is equal to integral dm from 0 to m. And so we can write this as m as a total mass of this disk, this ring here, my bad, m r naught square. So that is simple enough. And yeah, this axis that I'm talking about here is going into the plane of the papers or the page. So you can think of it as passing through you and going into the computer. So that's the axis that I'm talking about here. So this was our first case here. Very simple. We don't have to use integration. This is just to get you to help you get an intuitive understanding of what is being done here. So secondly is the moment of inertia for a long long rod of uniform density. So this is a rod, okay, over here, okay, and it's rotating about this point here or about one of its edges. So, and this edge is like going like this. I mean, this is the axis if it helps you visualize it better. So let this rod have a length L, okay, and it will have a total mass M. So what is very useful to do in cases such as these is define a standard by which we might be able to evaluate this element dm over here. So what people usually do is that we define a quantity lambda which is equal to m by L. Yeah, so we define a quantity called lambda, which is the linear density of this rod. We can think of it the same thing as, well, normal volume density, that is mass by volume, and we would be denoting it by rho. But here in this case we are writing mass by length and we are denoting it by lambda. So why this is useful is because we can use this to evaluate the mass of the small elements dm. Okay? We can write dm as the linear mass density, that is m by l, times an infinitesimal element at this point dx. Okay, so using this we can further evaluate the moment of inertia. So we're going to put the same the definition that we have here. So this is 0 to m over right now. It is dm r square, or let's use x square here because we've used x. So you have x square. And what I'm going to do is I'm going to substitute dm for this expression we have here. Right? So we're going to write this as 0 to L, because remember we're changing the limit from mass to length, so this will actually become x. So we are going to write m by L x square dx. So this is where we finally get into the integration. So what I'm going to write this as is I'm going to take m by L out because these are constant, and so we're going to write this as m by L and 0 to L x square dx. Now why I said it's better to be more familiar with integration is because this is here we'll be using the power rule. So we have m by L, we're going to put the limits x cube L cube by 3. Oh, it's supposed to be x cube, my bad. Yeah, and we're going to put the limits here. I'm sorry for that, but it doesn't make a difference, as you'll see soon. So this is m L square by 3. So this is the moment of inertia of a rod that is revolving about one of its ends, or rotating about one of its ends. So that's the second case done. So what we'll be doing next is the moment of inertia for a rod that is rotating about its center of mass. So we have a rod here, the same thing, and this is the axis. We are going to assume that this here is the center of mass. Okay. So it's exactly the same. We're going to define again lambda as m by L. Okay, and again we need to do dm as m by L dx. This is the same thing as just writing mass is equal to density into volume. What we're doing here is mass is equal to linear mass density into length. So for those of you who weren't exactly clear, I'm just getting it a bit more. So yeah, so we're going to write I is equal to again dm x square from 0 to m. However, when we substitute dm here, the limits are not going to be from 0 to L. Instead, they're going to be from minus L by 2 to L by 2. And the reason for that is this is exactly in the center of mass, right? So the distance to the left of it will be minus L by 2, and the distance to the right of it will be L by 2. That's why we are doing minus L by 2 to L by 2 instead of 0 to L. So we again going to have m by L x square dx, and when you evaluate it, it's going to be m by L x cube by 3, and this time is going to be L by 2 to minus L by 2. So when you evaluate the limits, you will have L cube by 24 plus, since it's minus, when you cube it will still remain minus, and when you subtract it will become plus. So L cube by 24, and when you finally write it out, it's going to be ml square by 12, which is again a result that is quite common. So that we have evaluated the moment of inertia for linear objects, but what about things like disks? So that's what we're going to do next. and I've run out of space here, so what I'm going to do is I'm going to go up all the way here and I'm going to move to the left. So let's begin. So while recording this, I've just realized that I've already crossed about 15 minutes and we still have both 2D and 3D objects left to go. So what I'll do is I'll finish the 2D objects in this video, and there'll be another video coming up shortly that includes the 3D objects. So which is mainly the cylinder, solid cylinders and hollow cylinders, and hollow spheres and solid spheres. So in this video I'm just going to finish it with by doing the disk example. Okay, so for disk we have which one is this? Is this fourth? I think, yeah, this is fourth. So for disk it's slightly more complicated, but it's still quite doable. So what we're going to do is we are going to have an oval here. Okay, and let's fill it with yellow this time, I guess. Hold on. Okay, I don't know how to work with paint. I don't know what I'm doing. Yeah, let's fill it with yellow here. And so we'll change this color to black. And yeah, so we want to know what the moment of inertia of this object is about the center of mass. So again, what we're going to, but here we're going to consider defining in terms of densities, but instead of taking linear density, we're going to take area density here. So we are going to use the letter sigma, the Greek letter sigma, and what we're going to do is we're going to take the mass density, the area mass density, and this is sigma, and dm over here is going to be defined as m by a dA. Alright, so how do you get this dA element? Now that's pretty easy actually. So you have a over here, right? So a is equal to pi r square for a disk. So what we're going to do is we're going to take the derivative of this with respect to r. So dA by dr is equal to 2 pi r d, oh yeah, 2 pi r. So, and we're going to take the dr to the other side. So we have, although these are not exactly fractions, but it's helpful to consider them as fractions in a lot of places, so that's what we're going to do here. So we're going to write this as 2 pi r dr. Alright, and there's another way to visualize this. What you can do is you can consider a small ring of mass dm over here. This is supposed to be a ring. Okay. Alright, so I'm just highlighting the fact that this is a ring. Oh god. Alright, so let this have a thickness dr, alright? So, and let this be at a length r from the center. So what we are saying through this is essentially that the area of this ring over here can be considered as its perimeter, that is, this is 2 pi r times dr. This is the same thing as evaluating the area of a rectangle, right? This is basically length into breadth. So the perimeter can be considered as a length, and the breadth can be considered as the thickness. So the area is nothing, the small area is nothing but 2 pi r dr. And the radius is going to remain approximately constant because again we're talking about very small lengths, dr. So we're going to write dm as m by, or you can write sigma. Yeah, I've realized I've actually used lambda or sigma before. I've just written them as m by l, but you get the gist. So sigma 2 pi r dr, right? And then again we're going to pull out our moment of inertia definition. I is equal to dm r square, and of course the area over here is pi r square. That is the area of the disk. So we can write this as from 0 to m sigma 2 pi r cube dr, because there is already an r square over here. Yeah, so we can take sigma out because sigma is a constant, and we can also take 2 pi out. So we have 2 pi sigma, and this is actually changed the limit because this shouldn't be r, this should be r naught here, my bad. So this is r naught here, so we have r cube dr. So again we'll expand this to pi into m by pi r naught square, because that's the area. Yeah, it's pi r naught square. So we'll cut the pi's, and this can be written as r to the 4 by 4 r naught and 0. Since the other limit is 0, we can simply write that as 2m by r naught square into r naught raised to 4 by 4. 1, 2, and we'll cut the power right over here, and this gets fully cut. So this is actually equal to m r naught square by 2, which is the moment of inertia of a disk about its axis. So I hope that was helpful. If I did go a bit fast, which I think I probably did, please do let me know, and I'll try to slow down in the next videos. And so there are also moment of inertia of a rectangular plate about its axis and moment of about its moment of inertia, about its center of mass. My bad, about its center of mass and about one edge, but that is quite similar to this one, the one for rods and the one for a rod about a center of mass. So I'll leave that as an exercise to you. So do let me know what results you get. So with this, I think we come to the end of 2D objects. Okay, the other 2D object was the ring, but the ring is quite simple, as you've already seen. So in the next video, we'll be looking at how how to derive the moment of inertia for a cylinder and the sphere. This holosphere is actually the most complicated, I believe, but it's actually quite interesting as well. So I'll see you there. Thank you.